we're going to get started in our new unit, which is based on something that is insanely fundamental to statistics. And that is being able to compute the probability of an event, because then we can tell and quantify if something is unusual or not, which then allows us to make conclusions about certain things. Okay, so that's kind of the long term direction we are headed. But we have to start with finding those probabilities. And so, what we're going to do is start with the idea that you're already familiar with. Say finding the probability of something you know how to do, like find the probability of the landing on each die of the face or face of a die. So, that's 1/6, okay? Because we've got 1/6 of the time you're going to land on a 1, 1/6 of the time you're going to land on a 2, and so on. So, a couple of things about this. You can see that this is uniform in shape, if you remember that word, uniform, and that's because all of the events are equally likely. Okay, so it's uniform because of that. This also happens to be what we call discrete, which isn't majorly huge that you get that vocabulary right now, but it is worth talking about. This is a bar graph because you can just have these particular events. I mean, technically, I could rearrange these in any order. I don't have to have them from least to greatest. Okay, now as you can see, if we had more possibilities, say if we were talking about the probability that you would get a particular type of card, well, there are 4 of each type of card, and there are aces, kings, queens, and so on. So you can see this is divided into smaller sections because we have more options, more possibilities. This is still discrete, though, because there are 13 distinct possibilities. Now, let's bridge into something that is called continuous. So, if we think about drawing or throwing a dart at a dart board, okay, if you think about throwing a dart at a dart board, there is so many infinitely many possibilities that that dart can land on that board. I can't really divide it into, 13 distinct possibilities. So there are all of these different, so like if you can imagine each little piece of color pigment or pixel in this picture is a dart hitting the board. Now, this is showing that it's the same equally likeliness to get to the center of the board to the outside of the board. Okay. I don't wouldn't necessarily know if that's true, so that's interesting. But in this case, they're showing that the dartboard, if you just I guess did random and not go for the middle, you would hit it the same across all locations in the board. Okay. So the idea is that, um, you know, first we mentioned these probabilities, but we're showing these probabilities as an area. Okay. And so that's kind of an important thing that we need to, the first thing that we need to kind of bridge into. And that is that we can represent the probability of an event based on how much area it takes up in a shape. Okay. Again, in fact, I'm going to write that down because that's really important. And I think that might even play into the reflection that you do today. Um, we can determine the probability of an event. We can determine the probability of an event based on how much area that event takes up in a shape. Okay, so see here, whenever we've got, uh, you know, so then we've got the continuous versus discrete based on if there's distinct amounts versus continuous amounts. And of course, these were uniform because they showed equally likely possibilities. Okay, So let's take a look at these two things here. How would I calculate the probability of landing in the shaded area? So if I were to throw a dart, and here I have this shape, this rectangle, what's the probability that I would land in the red section? Well, since the red section is 40%, and then this goes all the way across to 1. Now, this is interesting. It is not drawn to scale, but this is 1 high. And the reason I know that this is supposed to be 1 high is because what's all of the possibilities combined make up how much probability? All possibilities, of the events make up 100% of the data. So 100% in an area is 1. So with this rectangle, length times width is 1. Okay? And so that's how I know that this had to be 1 high because we had to have 1 times 1 giving me an area of 1. And then how much area is shaded red? Well, I can see 40%. So 40% chance of landing in that shaded area. Now, this other shape is interesting because notice it is too wide. But it's so if it is too wide, then it's only a half high. So this one is probably still not drawn to scale, but uh, how would I then compute the area of this red section? Well, it's length times width. Okay, so then this from 0.6 to 2 is a distance of 1.4, and 1.4 times a half is 0.7. So this area is 70% of the shape. So the probability of throwing a dart and randomly ending up in this area is 70% chance. Okay, so shapes 100% of the data, and that the shaded area or whatever is that probability of being in that section. All right, next page. So then let's kind of talk through what we just learned. We said that the total area of a probability distributions was 1 because that probability that it's going to happen is 100%. Therefore, that total area under the curve is 100%. Okay, now let's talk about shapes that are not rectangles. Because you know what? Truthfully, real world data isn't all uniformly distributed. Everything is not equally likely. Okay? So we end up with things such as this. A lot of times the thing that is expected is more likely to occur and is going to happen more frequently. And then you have things that are farther away from what's expected are going to happen less frequently. Now, take a look at, see, here is a situation where we have a histogram with 7 intervals. Here's one where we got 36 intervals. So look at kind of what happened from 7, it's kind of clunky, 7 sections that we could find those areas for versus, smaller little sections. Looks a little bit more smooth, a little bit more continuous. So what happens is as our intervals, as our the heights, the histogram, the bars in the histogram get smaller and smaller and smaller, then we have this more smooth, continuous shape. That idea kind of is having to do with a continuity of and calculus, where we would then integrate an area. So we see it then starts to behave more normally. Now, this kind of gets mathy here, and I'm not going to go much in depth to it, but just to show to you that it has been determined that the normal probability distribution is this actual function, this equation. And so I went and put it in my calculator just so you could see. And then here's how it graphed on my calculator. And so the idea is that you can see here, this is the normal model with the mean located in the center, and then we have 1, 2, and 3 standard deviations down below, and 1, 2, 3 standard deviations up above. And so that is, remember how we said if you're more than 2 standard deviations away from the mean, you're an outlier? Well, now we can start computing what is the probability, what proportion of data is in that section. And that's then where we're headed with this next. Okay, so here we go. Questions about the normal model. Where is the mean and the median? Okay, so because of symmetry, remember, because of the symmetry, then we have got that those things are in the same location. The mean and the median are going to both be in the center because of symmetry. All right, what do you think is going to happen to this curve as that standard deviation gets bigger? What's going to happen? Remember, a standard deviation is the average distance from the mean. So then it's going to spread out, become more varied, get flatter. All right. How about the total area under the curve, which we already talked about? That is that 100% or 1. Oh, this is interesting. How many standard deviations wide is the normal model? Well, you can see we're going 3 standard deviations below the mean and 3 standard deviations above the mean. So that is 6 standard deviations wide. All right, so you know what? If I told you the minimum and the maximum of data and I knew, and it was normally distributed, then you could approximate the standard deviation because you could know that there's 6 standard deviations from that min to the max. Okay, so interesting there. All right. Can you compute the area under the curve between the standard deviations 0 and 1? So let me see if I have a picture down here. So if we were to literally come up here and try to compute this area in this section, we don't mathematically have the tools to be able to do that. And the reason is because of this is not a perfect rectangle. It's got this curved shape. So I don't have, I could break it up into rectangles and such, but then that wouldn't be completely accurate because of this continuous curve. So guess what? Calculus to the rescue. Calculus, and that's what that subject does, or one of the things that it does for us, is it can compute the area under the curve. It can integrate that for us. And so, but we are not going to have to do the math to it. We just have to kind of memorize and learn some of the common numbers that calculus has computed and integrated to find those areas. So here they are. So calculus has computed and it has found that the area under this curve is 1, that the area within 1 standard deviation, so from 1 standard deviation down to 1 standard deviation up, this section here, including that curve at the top, so this is 68% of all the data. So when we talked heights, if you are within 1 standard deviation of the average height of the students, you're in the middle 68%. That's pretty not unusual. Okay, now if you are within 2 standard deviations, then you are in this area, and calculus would compute this area here. It would integrate it across that function from the 2 standard deviations down to 2 above the mean, and then that would be 95%. Now these are approximate, so that's about 95% of the data. Then the third item we would have, if you're from 3 standard deviations down to 3 standard deviations up, and you computed this area with calculus and you integrated to find that area under that curve, you would have 99.7% of all data that are from the normal model, if things are distributed that way, should be within 3 standard deviations of the mean. So there are some extreme data sets out here in an extreme amount of data out, extreme data out there. If it's really far away, it's more than 3 standard deviations. Of course, we've kind of talked about how even just being above 2 standard deviations are outliers. So we're going to talk about how much data that is. And so in order to do that, we need to then kind of be able to work our way around more than just these middle sections of 68, 95, and 99.7. So that's kind of some key numbers you got to know: 68, 95, 99.7. It's also sometimes referred to as the empirical rule. Some disciplines or careers or whatever, they'll refer to it as the empirical rule. When my dad went to school, that's what they referred to it as, was the empirical rule. But also somewhere people started saying, it's that 68, 95, 99.7. So interesting there. Okay. So the next thing that we're going to do is we're going to start talking about how to work your way around the sections of that and computing the individual little pieces. So so I should be able to determine how much area is just in that little section right there based on the fact that from here to here from here to here is 68%. Okay, so then figure it out. What is this? Well, I can tell that that's half of it. So that's 34%. Okay, so that's how I'm just gonna go ahead and write that in there. I can tell that that's half of it. So that's got to be my 34%. Okay, well, then of course, here's this one, 34%. Okay, now can you get these ones here? Say, like in this section here, from -2 to -1, or +1 to +2. How could you figure that out? I'm going to go ahead and put this color in here just so I have that colored also. Well, in class, I'm going to let my students kind of stew on that and see if they can't figure it out, because I think you can. I think you're smart enough. I think that if from here to here is 95%, what if I take out this middle section that I know to be 68%? So what is that taking out? How are you doing the taking out from that 95? Well, I'm going to do 95 minus 68, and that equals 27. So what that tells me is that 27% is located in that section and that section. So that together makes that 27%. Okay, that 27% right there. Okay, so then hopefully you can figure out from there, if those two pink sections are 27% total, then I'm just going to do my 27 divided by 2 to come up with what that is for each one of those sections. So 27 divided by 2 is 13.5%. So that is why each one of these is 13.5%. Okay, and then this one here is 13.5%. Okay, so now let's keep going. Let's figure out the sections next to them. Going to use the same idea. So I want to go from 2 to 3. Okay, I want to do this little section from 2 out to 3, 2 out to 3. Okay, well, what my brain says is, hey, from here to here is 99.7%. Okay, I want to do 99.7%, and I want to take away the part I've already computed here. I want to take away this 95% in the middle. So that's what I'm going to do. I'm going to take my 99.7 and take away the 95% in the middle. And when I do that, whatever it is that I get, let's see here. 99 Yeah, there we go. 99.7 minus 95 equals, what is that? 4 point, what? Something is not making sense. 4.3? Something is messing with my mind here. 4.7? Yeah, 4.7. I have trouble adding and subtracting. I'm sorry. Okay, 4.7. All right, there we go. So, what that tells me is that 4.7 is what remains between those two little sections. Okay, so 4.7 remains between that section right there and that section right there. That's a total of 4.7. So, how do I figure out what is in each one of those things? Well, 4.7 divided by 2, and that equals my 2.35. See, I can do that dividing easier than I can do that subtracting. Okay, so that puts 2.35% here and 2.35% here. So what's interesting is there's still some data left in the very, very, very extreme outside edges that goes out past 3 standard deviations. Okay. Well, how much is that? Okay. There's a couple ways you can think about it. One way is, okay, this has got to be 2.5% because there's 95% in the middle. So then you could take away the 2.5 minus 2.35, or you could also do like we've been doing, which the way we have been doing it is we do 100 minus 99.7, and that equals zero point 0.3. And then so that's zero point 0.3 is what is left between those two sections on the very, very tippy tips of the normal model that go way out to infinity. And so now we then take that point 0.3, divide it by 2, point 0.3 divided it by 2, and that equals 0.15. So each one of these have so much, teeny, teeny, tiny amounts, less than a fifth of 1%. Less than a fifth. So if you were more than 3 standard deviations out, whoa, you are very unusual. Like if you had a height that was more than 3 standard deviations above the mean, holy moly, you are in the top 0.15% of people's heights. Okay, so that then makes up what we have right here. Here are all of those sections that we figured out, kind of written a little bit more cleanly for you. There are the sections, probabilities of the normal model when you are a whole standard deviation distance away from the mean. Okay, so now what we're going to do is just go ahead and apply this. I'm going to go ahead and break this video down into 2 sections. I think it's easier when we do that. So I'm going to stop this one right here, because where you're going to go next is then take all of these ideas of these percentages to a real world situation and find the probability of events. So, in between me starting the next video, I want you to come on over here to this and label this. This is about the distribution of the heights of college women. It has a mean of 65 and a standard deviation of 2.5. So, let's think about that. That means right here in the center is 65. Okay? So, what height of a woman is if she is 1 standard deviation above the mean? Well, I get that from doing 65 plus 2.5, and that's 67.5. Right? So, that is what the height of a college woman is right here. So, are these inches? Yeah. So, these are the height of height of college women in inches. Okay. And so what I want you to do is take a moment while I switch the video and do all the computing. Figure out what is on each one of these standard deviations. See, 2.5 up would be 70 inches, and then 72.5, and so on. What I also want you to do is fill in what we just did earlier, where you list the percent of data that falls in each one of these sections. So I want you to label what percentages are in those sections there. Okay, so you put some math to it, figure out those sections, and I'll meet you in the next video.